Hello, everybody. I'd like to welcome you all to this next brown bag webinar of EarthShift Global, and we're very happy today to have Valentina, who is pre-recorded here, but to just remind you who Valentina is, Valentina Prado is our senior analyst at EarthShift Global, and she brings extensive expertise in developing decision analysis tools for life cycle assessments and hands-on experience in the Sustainable Return on Investment, SROI, assessment methodology. Her focus has been in research and the incorporation of decision analysis to the interpretation stages of comparative LCAs and tackles issues of normalization, weighting, and uncertainty. And although this is pre-recorded, Valentina is here with us. She'll be taking your questions at the end. So I hope you will send all of your questions to me, Holly Harris, privately, and I'll ask them for you at the end of the presentation. So take it away, Valentina.
Hello, everyone. My name is Valentina Prado, and I'm a Senior Sustainability Analyst at EarthShift Global. This video is a presentation of the dilemma and challenges of reconciling values and facts in comparative LCAs. This is when we do a life cycle assessment with the intention of guiding a selection, but we find ourselves with trade-offs so that there is no single best alternative. So what can we do, and what are the challenges, and how to approach and think about this problem? This is a webinar that was scheduled for June, but due to technical issues, we had to find an alternative. So this one, it's that alternative. In the drawing here, the very professional schematic, we see, I think, what most LCA analysts would relate to, and that's the issue of trade-offs. LCA can be great in giving us that systemic perspective, but also we find often that the results are conflicting, meaning, okay, so what's the best choice for me, for my organization? And when dealing with environmental decisions in an environmental context, there is no single best answer. Often there is no single best answer. So I want to start with these two concepts. The first one, environmental sustainability is relative. It's not a check in the box. It's something, or a new version of a technology, or a new, let's say, revised version of a product may be better than the previous version, but nothing in absolute, let's say, it's environmentally sustainable. So one, environmental sustainability is relative. The results of an LCA, they're best interpreted on a relative way. They're multidimensional. When we apply a full LCA, I think one of the motivations is trying to keep that, that systems view, knowing that it's not just about carbon, but there are many different aspects of the environment that are important to us and important for suitable environmental management. And the third one is that it's continuous work. And we often say, sustainability is a journey. So that's the third point. In a comparative LCA, we are in a decision context. There is a decision that we're trying to inform, either a new product configuration, what kind of plastic should I use, or what kind of supply chain should I draft for this new product, how, we're trying to guide a selection, and that selection process is a decision. And when facing decisions, there's, some key points. One, that facts are uncertain. So on the other side, when we do the LCA, we know there's uncertainty. There's going to be uncertainty in our inventory, characterization factors, modeling, and there's, layers and layers of uncertainty, and the uncertainty that we don't even know that is an uncertainty. So we have to face this challenge. We have to make the decisions with the data and the information that we have, yet acknowledging uncertainty. That values can be in conflict, and this is when different stakeholders have different priorities. Some may prefer and prioritize water-related impacts, while others may be all about climate change. From the other side, we know that both of these things are important because environmental sustainability is multidimensional, but there can be different priorities. Stakes are high, meaning, these decisions that we're trying to reform are important for our product development, our marketing strategy, our evaluation of a certain market. They're important. They mean, something for the organization, and they have implications. And the fourth one is that decisions are urgent. Maybe not urgent, but they are in a shorter time frame. And basically that means that we cannot wait until reduce all uncertainties for us to make the decision. This is really what it means, so that we have to be able to make the decision with the facts that we have and our priorities. We may be wrong, but we need to strive to make the best decision with the information that we have. All right. So we do a comparative LCA. Here there's a set of environmental impact categories. The LCA community, in its effort to better quantify and provide better data, we're adding more and more categories to this, which is fine, but it doesn't solve the challenges of interpretation. And in this case, if we're comparing 3 products, we see trade-offs, right? Some are better in some categories, and that's with the green, or worse in other categories, and that's the orange. How do we what can we do with this information? And if you think about adding more indicators to this, it doesn't make our decision any easier. So we need to be able to find a way to take advantage of this great potential that we have to quantify information. But I think in that respect, there's a lot to be done. So we have our initial problem, and I leave it in hypothetical terms, and you can adjust it to your sector. So if you're in the paper industry, different types of paper or different processing technologies for paper, different feedstocks, or if you're in the electronics, right, adjusted to your sector. The problem is still a multi-criteria decision problem. We have, if we start here from the top, we have the famous bar chart, right? And this is maybe a little bit easier to look than the data table with the numbers and the different units. Here we get rid of the units, right, by scaling it to the largest, but we still see trade-offs, right? So, how do we make the decision there? We can try and make that axis, rather than horizontal, kind of concentric, and we get a spider plot. The issue is the same, we still have those trade-offs. Or there's some mechanisms in LCA, and that's going to be the focus of this talk, and that's the single score. How do we arrive at that single score? So in essence, right, the single score would mix all these things together and boom, generate this score, this index that it includes everything, so that the product with the lowest single score, in this case, it would be product C, that has the lowest impact. Boom. The other alternative is, let's say, oh, this is way too much, and I also don't trust the algorithm for the single score. We'll just make it all about carbon and defeat the purpose of expanding our worldview in the first place. So I want to talk about that single score, how it's done, and the aim of this talk, if I lose you later on, is we need to understand what's behind that black box. Some basics about aggregation. That is not the main field in our world, and people that are dedicated to this aggregation mathematics, they're not in LCA. So we need some sort of bridge, and that is my role. But yeah, so I want to talk about aggregation and how that's done. So this aggregation is done. The first step is, we have all these different units. What a mess. And then what we do with that is we normalize it. We, as I think people watching this video have done LCAs before, normalization references, they represent the impact of an average person in a certain community. So when we divide our impacts of our product to the impacts of that community, boom, we get a normalized result. Usually it looks something like this. If you work in CIMA Pro or other softwares, when you apply these normalization references, you see that boom, you know, many of these impacts kind of disappear, and we tend to call these relevant, right? So in this case, the freshwater and marine ecotoxicity are the relevant categories. To this, we add weights. We multiply by an importance coefficient, which meaning the higher the weight, the more important it is. But what I want to point out from the start is that look at the difference in magnitude, right? It's not that there is no fossil depletion or that there is no climate change. Is that the order of magnitude is so different once you do that normalization, that with applying weights to this, it's going to have very little impact. And I will show you that, but I can just tell you that from now. And the thing is that one of the main reservations against aggregation is adding weight and the values. But what we see from the studies that we've done is that the weights actually make very little difference because there's an issue in the normalization. And what we see is that this method altogether has some issues. So I will go over those issues. But okay, so here, you know, this is an example of what you would see in CIMA Pro or other softwares when you apply external normalization. And what one of our studies, this one is from 2017, found is that whether you're looking at solar energy, different electricity grids, or concrete mixes, paper, or even including all these different studies, when they applied recipe with normalization, these categories, freshwater and marine ecotoxicity, were the ones that, you know, were salient, were highlighted according to that normalization. If you look at the glass half full, you would say, great, this is very consistent. It doesn't matter what system I'm studying, I'm still gonna get the same result. If that's the aim, fine. You know, you've reached reach a method that is independent of what you put in. But that's not what we're looking for. We're looking to really evaluate each system. And not only that, but what we were seeing is that if we arrange the categories according to the coefficient of variation, so on the left, we have less uncertainty, that would be climate change, and higher efficiency, higher uncertainty. The categories with higher uncertainty tend to be the ones that are highlighted the most. So where we have the least information, that is what is driving our decision in the current method. We did the same study for CML and Tracy, and we found the same similar patterns where the same categories over and over would show up in studies for different types of inventories. So, all right, so this is just normalization results. When we add the weights, and for this study, this is from last year, we said, you know what, let's include all weights, all possible weight values. That is like if you have a space and every single point in that area, it's a possible weight value, right? See, being like climate change is 20%. No, it's 40%, it's 35%. And we'll just say it's all of them. Let's try all possible combinations of weights and see how the result changes. Here we evaluate results based on the ranking. So the lowest score, meaning the best, would get a rank of 1, right? And then we would switch the weights again. And then maybe climate change is not 20, but now it's 40. And then what's the score? Leads to X alternative still being, you know, first, so ranking 1. And that's what we see here at the top. The rank is in the x-axis, so being ranking first or second, fifth. These are different technology alternatives. And the y-axis is the likelihood of that alternative to occupy that rank. So in this case, we have the, let's say the brown, the ribbon silicon is most likely the best alternative, and amorphous silicon is most likely the worst alternative. This doesn't change when we change the normalization reference, Europe 25 or World 2000, which is contrary to what some guidance documents say, that they say, well, if you want to minimize bias, you have to increase the boundaries of your normalization reference. But we're not finding that. We're finding that the biases persist. If we look at, okay, what's behind that ranking, you know, how are categories playing together and shaping, you know, a ribbon silicon to be first or to be second? You know, what's the makeup of that? And what we find is it's the pattern in the bottom half. And visually, you just see that it's dominated by basically one category, and that's marine aquatic ecotoxicity. So you have this inventory, you do all this modeling, and you quantify performances in all these different aspects, but yet it's two categories that make up the scores. So there's a lot that we can improve from our current way of aggregation. So let's look at that equation that we have. So this is leads us to a really boring topic, subject line, in this case, methodological implications of a weighted sum, right? What I'm talking about here is understanding this magical pot, right? We are putting in the results of an LCA, of our LCA, and how are these being mixed? How are these being aggregated, right? What's the mathematic behind this without needing to be, you know, mathematicians? And what we have is a weighted sum. That's the name of the algorithm, and it's one of the most commonly used and basic forms of aggregating indicators. And this can work for some circumstances and some applications, but my hypothesis is that it doesn't work for decisions in an environmental context. And it doesn't work for at least 3 reasons, and that's the one that I call their fundamental challenges. So how this functions is you have your characterized impact, which is the result of your LCA. You divide it by the normalization reference, or you multiply depending on how that, basically you are dividing it by the impacts of something else, right? And then you weigh, you add a weight, which in this case is an importance coefficient. I must say that there are 2 types of weights: importance coefficient and trade-off weights. And this combination is considered wrong, inconsistent mathematically, because there's no notion of trade-offs. But I think that's outside of the LCA. So the weights in this case, it's like a cake, right? You have the whole cake of, this is the things that I care about, and then you split that cake according to, you know, how much you care about this different impact categories. So in the end, what I'm saying there is that the sum of these weights equals 1 or 100. Then you add these, and that's how you get the single score. So beyond data repairs, beyond, oh, this is out of date, which normalization references are, there are gaps, which there are gaps. But if in this ideal world with unlimited resources and budget for LCA research, there's going to be 3 challenges that are beyond data, let's say, perfection. 1 is linearity, 2, inverse proportionality, and 3, mutual differences. So let's go over these 3 challenges. The first one that I'm going to say is linearity compensation. If we look at how the result of this division behaves, it behaves in a linear way. So that as you increase your characterization impact, your characterized results, or you decrease it, the result of that division is linear. And this is linear forever, right? All of them. And what this means, this is because you see this linear trend, it's called a linear aggregation method, and this leads to full compensation. In decision analysis, you have two types of methods. Some are fully compensatory, like this one, that are linear. And in that way, you allow criteria to replace one another, to substitute, to compensate for one another. In an economic setting, this works perfectly, right? Lost profit and loss make up for one another, one-to-one. That's okay. But once you get into an environmental context, a sustainability context, can you trade improvements in climate change for degradation in water? It's like having these rollover points that can mask, that can make it all about one performance and mask other performances. An example of compensation gone wrong, like Brad Pitt, his eyes and those eyebrows, but would I compensate those eyes and those eyebrows for no teeth, right? Maybe I don't like him so much anymore, right? There's compensation doesn't apply for every context, doesn't apply for choosing a mate, and it doesn't apply for environmental management. Another example that I like to tell, and I sound like a broken record when I talk about compensation, is with grades. So let's say you have different courses that you're taking. If you can go back to your college days, let's say you do really good in one subject, so well that you have rollover points that compensate for the other lousy subjects that you don't like so much. And then you end up with the highest GPA in all your school. Does it really work that way? And in an environmental management setting, we want to be able to have this integral management, right? We want to be able to manage multiple things at the same time, not say, oh, I compensated this, right? I compensated Brad Pitt's eyes for the lack of teeth. All right, so I hope this image stays with you. There's also, I found online, a whole library of these things, but that's another subject. So one, compensation. So even if your data is perfect, your aggregation algorithm in this case is fully compensatory. You are allowing for that burden shifting, which is one of the main things that we want to avoid. Two, inverse proportionality. And I think the best way I can illustrate that is with this change of scale here. We have a huge ant and a tiny hippo, right? So depending on the value of the denominator, right, of that reference, if our impact of our system or characterized results compared to that reference, if it's a large issue, right, hippo, the result of that division is actually inverse, right? So a larger denominator is gonna give us a small result. And a small denominator, in case there are gaps or it's not a big issue, is gonna give us a large result. Meaning that we are systematically highlighting those issues that are maybe not as important, as severe, actually we have no way of knowing, or that the impacts that are, let's say, problematic for that reference wouldn't show up. And we say that this would be the moral equivalent of, you throwing trash and saying, well, it's not bad that I do it. My point of reference litters way more than I do. Right? So this inverse proportionality effect persists regardless of how perfect your data is. The third one, I like to call it common sense. We academics love to give terms to things. And it's basically, in a fancy words, is the degree of importance of one aspect depends in part on the difference between alternatives. So if you're buying a car, I think, if we were in a live audience, I would ask you what would be important to you. And what I find is that most people say cost, safety, cup holders. So let's say cost is an important issue. And I'm deciding between two cars, And if the difference in cost is not that significant, in this case $100, then maybe it's not so important for the decision. And this is common sense, and we apply this in our daily lives. But somehow we forget this when we are aggregating indicators. And this is the issues important in a decision is two things, right? Is what I care about. I care about my money, but it's also about what's the difference in the alternatives that I am presented with. And in this case, I may care about costs, but because my alternatives are so close in cost, it's not, it goes in the background. It's not an important aspect anymore. And we call this, in decision analysis, this is known as range sensitivity. Our current algorithm, our current weighted sum, does not take into account those mutual differences, right? Every alternative is evaluated separately in isolation so that these differences are not considered. And this, again, persists regardless of how perfect the data is. So these are the three challenges of the current aggregation. So what can we do differently? A decision in LCA needs to be informed by facts, things that we calculate objectively, right? There's always some value choices in an LCA process, but let's call them facts, right? Science-based, calculation, and values, what we care about. It cannot be just about facts, because then we'll have a machine making decisions for us, and it cannot be just about values, because then it depends on how I wake up this morning, and today I feel like product B, right? So we need, and then what's the point of doing an LCA if we're just gonna make decisions on a whim? So the point is to be able to incorporate these two aspects about the data and about our preferences and how they are dancing, right? In the current algorithm, we are seeing that there is a dominant player, and that's the normalization. It's not even about the data itself. What can we do differently? A proposal, and you may not need to apply the whole method, but look at the mutual differences. Think about comparative LCAs as a decision context, right? You're trying to inform a decision. So here we have different alternatives, and these are characterized results. We're not talking about aggregation, anything yet. And these differences, measure these differences with respect to uncertainty. And now uncertainty analysis, it's ever more accessible to us as analysts and practitioners. So here I have different options, again, with the PV technology, but you can think about, other alternatives. And let's do an uncertainty analysis, and let's see where my alternatives are very similar, so that they tend to, overlap. And in that case, that's supposed to be an indifferent phase. Like, if I choose the blue one or the orange one, they all have the same, let's say, effect in the environment. So I'm indifferent, whatever you want. Or as they start to separate, and you can start to discern one from the other, and then you may have a preference. You may like, okay, yes, I like this, or I don't like that. And depending on what you choose, it's going to have a more perceivable effect in the environment, because we see that the impacts start to be different. So what I have here is this is called trade-off significance, and what we did here is calculating that average overlap area as an indication of mutual differences. The thesis being, in a comparison, you want to identify where you have the greatest differences, the most significant differences between alternatives. It's not about an external normalization, but between them, where do you have the biggest differences? Here, this is a paper from 2014, and we compare this method with identifying issues with a normalization reference, and we find that the impacts that are highlighted with a normalization reference are the ones here in gray. So they are irrespective of that uncertainty. In this way, we are able to kind of base a decision and understand the trade-offs with respect to the level of uncertainty. So here at the bottom, freshwater eutrophication, that may be something really important to us, but if it's the same between all of them, because of the noise, because of the uncertainty, well, we cannot base a decision on this, right? This is going to have a lower influence in our analysis, in our decision. So I would say the number one thing you can do, and I'm gonna go on with a method, but the number one thing you can do, just look at the mutual differences. Look at, and the differences is where we want to focus a decision, because that's the knowledge that we have that going B or C is going to have a difference, make a difference. So taking this further, I'm gonna go over a method that applies these concepts of mutual differences, uncertainty, non-linearity for aggregating comparative LCA results. And this is called stochastic multi-attribute analysis, SMA. And what this does is, imagine each alternative is playing like a round robin, right? All of them against all of them, all pairwise possible tournaments, and like a round robin. So that, for example, here the blue alternative will play against the red, and they see how well they do relatively in terms of, in this case, water depletion or climate change or abiotic depletion and so on. This method also includes uncertainty. It means that for every run, we sample one performance of each. And then we say, okay, you know, this point from one and then the other one. Let's compare them, right? That's the range sensitivity. That's that. And how is that difference? Are they different or not? And there's some thresholds that we set. And we tend to set them as, if the difference is more than a standard deviation, then we can say, boom, it's significant. Or if it's less than half a standard deviation, then you know what? There is just not enough evidence that one is better than the other. This means that as you have more uncertainty and you have more spread of the data, you need a larger difference in order to prove, right, that it wins. And then one other visual thing that I want you guys to notice is this function here, this step function. It's not linear. So either an alternative gets a 0, being indifferent, it's a tie, or it gets a 1, right? And that's the maximum point you can get for in every single aspect. There's no rollover points. Once you get an A+, that's it. There's no A++, right? And this allows for a more balanced assessment where you avoid the results being overpowered by a single performance. Because having more of something doesn't make it better, right? And since we are in a management problem, we need to be able to balance the different performances. So that's what we ensure with this algorithm here, with this function. As we can see, it is not linear. And this method in the decision analysis is called outranking, and it belongs to the family of partially compensatory. No compensation means no decision, nothing, right? You just are left with midpoint results. So we make a compromise, right? We have to make a compromise. Otherwise, we are left to our preconceived notions. We are left to our, first impressions. And there's all these cognitive biases that we are subject to when dealing with, this big data table. So we make a compromise and we apply a partially compensatory approach. So in this case, we don't have the inverse proportionality. We're not using normalization references. We are including the range range sensitivity because we are looking at the mutual differences, and we are limiting the amount of compensation so that maybe my my partner wouldn't have those lovely eyes, maybe not so great, but it would have teeth, right? So it's a balance. It's a compromise there. So that's this is the normally, like, let's say the scaling portion of that method, and scaling according to the mutual differences and according to uncertainty. The second portion of it is the values. And as I said, with the previous experiment, we applied stochastic weights. These are also importance coefficients. But instead of saying, okay, you think it's 10 and you think it's 40, so we do 25, and then that 25 doesn't represent the person that thinks it's 10 or the person that thinks it's 40. It's just it's equidistant to any truth. We say, okay, we'll sample 10, we'll sample 45, we'll sample everything in between and see what the result gives us. We can either go for an all-inclusive approach where we see the different functions here overlapping. Each line is an impact category, so that we're not giving a preference to any impact category, so that we're sampling the space for all of them with the conditions that the sum equals to 1, or I guess 100 in this case, and that the values of each weight range from 0 to 100. With those two constraints, we can sample all possible values. They may be real or they may be not, but the thing is that we rarely know what the values are, and there is no right value. So let's have like this sensitivity and see, all right, let's explore the entire weight space and see what happens. It is also possible, like we see here in the right, that you have a preference. Either your business organization has very clear, carbon targets, water targets, ecotoxicity, and that you want to give those aspects preference so that we shift that distribution towards the right. In this case, we're systematically sampling higher values for a certain impact category. So that is possible too. So we can play with the weights and seeing, well, under what circumstances would, let's say, product B would be better? Well, in this case, you would have to have these values. And then we find whether that is acceptable or not. This is also useful for multiple stakeholders. We can run an assessment on each stakeholder and see at the end what is a good compromise, right? Is alternative A, according to their different values, is it an acceptable compromise for them or not? But we are moving away from that average, right? From reducing different sides of the spectrum to a medium point that doesn't represent any of them. Or the equal weights, which is quite often applied in LCA, but equally shared, that would be kind of the median here, but that's again also a very narrow view. So I showed you another version of this. So earlier in the presentation, I showed you this slide, but I didn't show you the outranking, the SMA results. So here we compare the same alternatives, the same weights, but different scaling, so normalization or outranking, and seeing how that changes the order of alternatives. And what we're seeing here at the top is that according to outranking, cattail is better, and single silicon has, the least preferable performance, overall performance. And if we look to the lower bottom of the slide, it looks like just an entirely different picture, right? This impact category contribution. In outranking, you get a wider participation of the different impacts. It's no longer just about marine aquatic ecotoxicity. It's about all this other range of issues. And in fact, if in this paper, we show the midpoint results, and we see that cat-tail is either the best or second best in most categories. And yet, when you do the single aggregation with the current method, it doesn't show up, right? Because it's all about that one aspect. So here we see, there's an advantage of looking at mutual differences, looking at uncertainties, and having a result that is inclusive of these different aspects that we're trying to manage. So I'll go back to the start of the presentation and say, environmental sustainability is relative. And in this case, I think it's key to, in a comparative LCA, relative, right? It's comparative. Compare the alternatives with one another. See where the mutual differences are. That is multidimensional. And this is about, trying to consider the aspects that you're quantifying in the first place before kind of shortening to carbon, which is, or climate change, which is often what happens. And that, decisions, when making decisions, facts are uncertain. And in this case means that uncertainty analysis is ever more accessible to us as practitioners. So in comparative LCAs, this is a great way that you can use uncertainty to evaluate those mutual differences. When it comes to values can be in conflict, I think applying a method like SMART can help reconcile these different values, trying to identify what's a suitable compromise and making decisions, right? So having that ranking, considering the different levels of knowledge, right? So that if something has high uncertainty, like toxicity categories tend to have, that we don't necessarily have to exclude them from the beginning. Oh, this is too uncertain, I exclude it. But if they are still important components to the decision, that we can bring them in, but consider that uncertainty. And that's something that SMA allows us to do. All right, I think that's all. Thank you very much for your time, and I hope that you learned something from this. One, let's really have some awareness of what's behind that single score, have some idea of those general principles and why that weighted sum doesn't work for environmental and sustainability applications, knowing and being less scared of uncertainty, and actually uncertainty can help us guide a decision. This is a method that is documented in the literature. We have applied it in different contexts. The method was recently published in environmental software and modeling, where we describe this one here, Prado and Huygens, where we describe the step-by-step process of this method. It is more complex than the single score, than the weighted sum, but I think that investment pays off.
Thank you, Valentina. How interesting and challenging, I would say. We have some questions for you, and the first one is, unfortunately, but not surprisingly, that most uncertain categories contribute most to decision-making. Can you think of any examples of decisions based on these and outcomes that illustrate the differences in decision on different aggregations, especially any before-after views? Essentially, she'd like to see how incorporating alternative approaches change environmental decisions and what the process is to selecting weights.
Thank you, Holly. So on that first point, whether we can test different approaches and see whether there is a difference in outcome. There is a publication last year called Weighting Sensitivity in Life Cycle Impact Assessment in the Journal of LCA, and there we test the conventional approach, and I think actually, yeah, I did show some figures from that paper in the webinar. And we see how testing different in aggregation approaches, the ranking is affected. In this paper, and I think there is another paper, I think Werf et al. It's cited in the literature review. They look at different aggregation approaches, particularly looking at different normalization approaches. They don't include SMA, but they do like internal normalization, normalization by maximum, normalization with a reference, and they find that the normalization approach, whichever, if it's internal or external, by a minimum, by a max, division, it has the most effect in the results. So that when we think about weights, the idea is that these weights are in relation to that normalization step, which we usually think about these two in a separate way. In terms of how to select weights, in decision analysis, there's two types of weighting. One, which is the one that we're most familiar with, is importance coefficient, and that's kind of like the pie, and then you share it. The other one is trade-off weights. And what depends on which approach to use, it depends on what a preceding normalization or scaling approach you are using. If your preceding scaling approach considers these mutual differences, technically, then you should be using importance coefficients, which is what we're doing in SMA. So in that way, the weighted sum, it's an error, it's an analytical error, because the normalization step doesn't take into account those differences. So how to choose weights is one, what type of weights it's appropriate for your algorithm, for your sum, for your aggregation. And two is then how to elicit those preferences. And that, you know, the area of weight elicitation it's an entire discipline on its own. But what I'm saying is that at least it should be mathematically appropriate.
Okay, thank you, Valentina. I wanted to say that I loved all your graphics. I think your humor is very funny. Someone writes, SMA is very interesting. And what about using damage instead of characterization, or just use damage to get beyond trade-offs?
At damage, if you get the endpoints, you may still have trade-offs. You would still have, and these trade-offs, you wouldn't know, okay, how much of a difference can be considered suitable or enough for making a decision a certain way. If you are this form of aggregation, so you go from midpoint that has different units to a damage category and converting everything to human health or dailies. It is true that you can deal with trade-offs that way because you end up with one single metric, but then the question is whether we trust that conversion from midpoints, which is already an extrapolation of that of the potential environmental impact. We go from release of a certain chemical to the potential environmental impact. There's already some sort of, fade and exposure modeling of what that may incur in the environment. And then to damage point, it's even, further steps. And I think that when I look at those conversion steps, they seem way too simplistic. So that I think that there are better ways that we can aggregate these multiple criteria with different units in a better way. I think SMA would be a better way than damage, because I don't trust. Because I think that conversion process it adds too much uncertainty, and the modeling there is, there's more factors there that you're adding.
So when do you know when to apply SMA?
Thank you, Holly. There has to be trade-offs, and you have trade-offs when you have a comparative assessment. So you have A, B, C, you have multiple alternatives. And as these little kids drawing there shows, right, you have these trade-offs. Something is better at something but worse than another. Then you may apply SMA. If there's no trade-offs, if you have an option that is better overall in everything, then there's no whatever category you're looking at, there's no conflict, you have a better alternative. Even if you have trade-offs and you may interpret results at midpoint, you may still get a valuable insight. But in the event that you need to make a selection and you're really struggling with, should I pick this one or that one? Should I, go with this type of plastic or this other type of plastic? Then in those situations, if there's a decision in mind beyond, understanding what's going on, I think SMA would be an appropriate interpretation aid.
Thank you. Would you please tell me what limitations there might be of the method?
Yes, there's always limitations. The number one limitation, I think, as I said, it's more complex, right? The weighted sum, it is one of the most used ways of aggregation because it's simple. So SMA is complex. You need uncertainty analysis, and also you need to apply this algorithm that is not easily accessible. Even though the equations and everything is published, it is not easily accessible. That's number one. And I think with that comes knowledge about it, confidence in using it, confidence in interpreting. That's one of the challenges.
Thank you. Is there an optimum context for the application of SMA?
I think so. I think so. Whenever there is the motivation of a decision that aims to select among conflicting alternatives, which is what we often find in environmental and technological solutions, that there is no silver bullet. These options are abundant, right? That there's no single best option, and that's what we find increasingly as we look at multiple environmental impacts. So whenever there's trade-offs, cases of high uncertainty, where you would be, let's say, you would have more motivations to quantify uncertainty, like new technologies, whether you have uncertainty around how the technology is going to perform, how so efficient it's going to be, maybe between 5 and 15% efficient, the yields, and this is why SMA has been kind of used or discussed along with discussions on anticipatory life cycle assessment when you have emerging technologies and you have high uncertainty and you have this kind of comparative technology.
Well, I think we have time for one more question. So I will say, given your critique, can normalization references improve to be more useful?
I think that this is a good question because this is what the community of LCA that is working on normalization references is trying to do. And they're trying to make it more useful by updating them, by filling in gaps. But what I'm seeing, or what I've found through my research, is that the purpose of external normalization for aggregation and its limitations are beyond how perfect the data set is. So we keep we still have this agenda in normalization, and I see this in the CTAC groups, which the agenda is the same, to have better normalization references, and we're focusing in the value of the normalization references, how updated it is. Maybe I think recently some of the goals is to include uncertainty in the normalization reference, but it's still going to be applied in this context for comparative LCAs. It is still going to be a fully linear algorithm. You're still going to have compensation. You're still not going to look at mutual differences, even if that reference improves. So I think normalization references fulfill a purpose, like benchmarking for different regions, for instance, but I don't think it's suitable for aggregation.
Okay, thank you. And thank you so much for joining us from Colombia all the way. And so happy you didn't get hit on the head with any guavas while you were
Yeah, there was
sitting there.
one that just fell down behind me. I'll catch
Uh,
it after the call.
all right. Well, thank you all who joined us, and thank you, Valentina, especially for your very interesting and complex presentation for us. And we'll let you get on with your days and hope you all will join us next month for our next Brown Bag webinar. Thank you.
Bye.